Welcome to Cybersecurity from Scratch, Technical Foundations, Episode 2, Enumeration, Mapping and Managing Technical Attack Surfaces. This episode is going to open with a basic primer on how modern networking operates, and then we'll turn to looking at how red teamers can map that network with a variety of tools. We'll talk about digital services and how red teamers discover them. And from there, once we understand the red team side, from the blue team perspective, we'll look at how we can manage our attack surface with regard to the network, and how we can apply defense in depth principles to ensure that we're protecting our systems. We'll also look at limiting information leakage from the perspective of what the red teamers are looking for, so we can counter the tools and techniques that they're using. The Internet Protocol, or IP, provides the backbone of modern networking, including, unsurprisingly, the Internet. The basic idea is that there is an address used to identify a particular host and a port that identifies the service that you want to talk to. So a client will use these two pieces of information together to try to talk to a particular service, for example, a web server or an email server, etc. But there's two protocols that are built on top of IP that provide the actual data exchange. The first of these is the Transmission Control Protocol, or TCP, which provides reliable communication. What this means is that the client will always know if a message got to the host, and it will always know that the messages it sent arrived in order. However, there's also the User Datagram Protocol, which is faster, but doesn't necessarily inform the client if all the messages got there. They may not always get there in order, and in short, it's just not always reliable. You might think this isn't very useful since you don't necessarily know if your messages got there, but there are some applications, for example streaming video, where it doesn't really matter if all your messages got there. The idea is that it's fast and most of the data gets through. IP addresses allow information to be routed to the correct host or computer that the sender wishes to send a message. The older and more dominant form of addressing today is IPv4. Where you have a 32-bit number representing the address, but for the sake of the humans involved, we break this address down into 4 numbers ranging from 0 to 255. For example, every computer has a loopback address, or an IP address that allows it to talk to itself, say if one service on the computer wants to talk to another service on the computer. And this address is 127.0.0.1. Now you'll note that I said this is the dominant form of addressing in the world. However, a 32-bit number will only give you 4 billion-ish addresses, and we've got about 8 billion people and a lot more devices than that. So how do they all talk to each other? Well, as it turns out, there's some technologies that make it so you don't necessarily have to have an address for everything on the internet in order for everything to talk to itself, but we'll get to that in a few charts. There's also IPv6, which originally was supposed to be the solution to the whole running out of addresses thing. But they might have overdone it a little bit. So with an IPv6 address, you have a 128-bit address, which certainly you are never going to run out of addresses for devices for people on the planet. But at the same time, you then have an incredibly unwieldy long address. So you have 8 groups of 4 hex characters, and it's kind of a mouthful, and that's way more than anybody can remember. It definitely is useful, and at some point we'll probably all have to migrate to IPv6, but for now, we're kind of limping along with IPv4, and there's a lot of people who want to keep it that way. While everybody who's using the internet is using IP addressing, the vast majority of people are not remembering IP addresses. You could, but that's really inconvenient, and so we don't. Instead, we have something called domain name service, which allows us to take a good human-readable name and translate that into an IP address under the hood. So the idea is, take for example, you're visiting the English version of Wikipedia, where you're looking at en.wikipedia.org. So the domains are proceeding in specificity from left to right, where at the top level you have .org, which is the top level domain. And then Wikipedia is a subdomain of org, and then en is a subdomain of Wikipedia. So the idea is that your browser is able to use DNS to look up the IP address associated with that particular domain name. Subdomains are not necessarily different hosts. So for example, there's obviously not one master server for all .org addresses, and Wikipedia is just one service off of that. You know, Wikipedia has its own servers. But EN is not necessarily a separate server from Wikipedia. Sometimes different web servers will be set up to respond differently depending on which subdomain they're addressed as. And so this is a real part of the exploration process for a network, figuring out what all the different available subdomains are. Sometimes there will be different services that are sort of hidden behind subdomains that might not be obvious to an attacker. Now, this is a trick that often gets used in capture the flag exercises as well to sort of drive home this point, where you'll have a web service running in the target host, but what you're really supposed to do is find out that there's a hidden subdomain or something like that to find some secret. And this isn't some gimmicky thing. Like, this is actually fairly representative of the real world, where often you'll have like an admin version of a website or something like that that unlocks, some hidden controls or something. It's fairly realistic, and it happens all the time. Now, with an IP address, we're able to route traffic to a particular host, but from there we need to figure out which service we want to send it to. And for this, we use the port. So when you start up a new server, say a web server, you need to tell the host which port you want to listen on. Now, in the case of a web server, you're probably going to be using port 80 if it's unencrypted HTTP. Ports fall generally into three main groups. Ports 0 to 123 are reserved for essentially universal services. For example, HTTPS servers are almost always running on port 443, and SSH is running on port 22, etc. And these ports are just sort of assumed. So often when you're using, some terminal program on another host and connecting into a particular address, it's just sort of assumed that the reserved port is the one that's being used. For example, port 69 being used for TFTP, a lot of times with the protocol, you don't have to say you want to use port 69. It's just kind of assumed. Above that, you have the port range 1024 to 49151, where you can, as a company, register that your software will use one of these ports. And this just sort of helps industry deconflict the use of ports so that you don't install two pieces of software and they're all competing for the same port. Now, above that, you have ports 49152 and above, which are just sort of dynamic or private ports. So if you have some internal company service, it's usually safe if you just pick a port above 49152, and you're going to be okay. You're not going to have a conflict there. Now, in terms of networking, we often use the term socket. Now, this is a software construct for sending information over a network connection. So, for example, if you're writing a Python script, you'll have a socket which allows you to bind to an IP address and port for networking. And we're going to get into this a bit in some of the later episodes when we use some Python scripting to actually try out some of the techniques that we're using. But just know that when we use the term socket, we're specifically referring to the software construct, and that's distinct from the address and port information. One of the most basic tools that we have in networking to figure out if one computer can talk to another is the ping command, where we'll say ping and then the IP address or the host name that we're trying to reach. And what will happen is an ICMP message, or Internet Control Message Protocol message, is sent out to that host. And if it's able to route successfully, we'll receive a good response. If not, then we don't. All the network equipment in between that's built using IP is able to respond with these messages. And so if an address is unavailable, it's sort of smart enough to know to route a negative acknowledgement back to you. Now, something to know is that ICMP is a companion protocol for IP. It's not actually built on TCP or UDP or anything like that. So if you're a programmer and you're trying to write something that would receive ICMP messages on a TCP socket, it's just not going to work out for you. Along the similar lines, if you're using a program which can bind to a IP address and port and trying to use that for ICMP, again, it doesn't really work because it's built for a different protocol. It's not TCP or UDP. Let's actually start up a server and show a little bit of networking practice. So first, we're going to use a program called Netcat, which is going to be one of our best friends as we go through this series. So what we do first is we start up the server saying that we want to listen on port 1137. And then we're going to start up a client that's going to connect to that server. And we have our connection. So we can send messages back and forth. And essentially, these two programs are routing messages between each other using the address and port to uniquely identify which service should be communicated with. Let's go a layer deeper and talk about the TCP protocol that we just used to facilitate that communication with the client and server. Remember that TCP guarantees that traffic is in order, and if there are any packets dropped, that we detect them. So the way this works is as follows. First, the client sends what's called a SYN message to the server to start a new connection, and then the server responds with a SYN ACK to let the client know that it's ready. And then the client will respond with an ACK to fully open the communication. So at this point, we have an open session with the server, and from here on in, all communication goes out with a sequence identifier, and the server will respond to let the client know that messages got there. And vice versa, if the server is sending a message to the client, then the client will let the server know that a message got there safely. Let's repeat our little demo from before, except this time we're running Wireshark, which is a program that allows us to sniff network traffic and display the packets that are sent back and forth. So we start up our server. No traffic yet. Now we have our client reach out. From here, if we go to Wireshark, we can see first this SYN message that was sent out. And then we can see the SYN ACK, and then the ACK. So at this point, the client is talking to the server. So if the client then sends a message, we can see in quick succession, the client sends the hello message, and only a tiny subset of this packet is actually the payload. A lot of it here is all the headers and other information that TCP is using to ensure that the message arrives in order and that nothing is dropped. And then the server is saying that everything got there. So the server can respond. And we see the exact same thing happen where the message goes out and then the client says, yep, I got your message. And that in a nutshell is TCP. UDP, or the User Datagram Protocol, in contrast to TCP, is unreliable. Basically, a packet is sent to a destination address and port with no response or sequence identification, and that's basically it. There's no guarantee that it gets there. Now, this is perfect for streaming video where you need to just pump as much data out as you can, and so the overhead with TCP doesn't really make sense. Now, sometimes an ICMP unreachable message might be returned by the target if the packet can't be delivered, or if some of the network equipment in between determines that the address is unavailable, but that's not guaranteed. You might just be streaming data to somewhere and, it's going into the ether and you might not know. Let's try our little demo again, except we're going to be using UDP instead of TCP with Netcat. So by default, NCAT will use TCP, but if we give it this UDP flag, it will listen for UDP. And same on the client side, so we reach out. Now here we don't see any connection message, which is different. Let's check Wireshark. And I don't see any packets yet, so let's try sending a message. Now we've got the hello, but when we look on Wireshark, we only see a single packet here with the message. There's no response, there's no handshake, there's no nothing, just here's the data. And then the response, again, single packet, just has our data, and that's it. Much more lightweight than TCP. With the same transaction, we only had 2 packets instead of quite more than that. I think it was about 7, 3 for the handshake, and then 2 for each message. So 7 total versus 2 packets, so much more lightweight. But at the same time, just fire and forget the data. Maybe the packets got through, maybe they didn't. It's all sort of up to the application to enforce any, controls that it might need on whether or not the data gets where it needs. It's not built into the protocol. Firewalls are one of the most basic networking defense tools that we have. Essentially, the firewall processes incoming and outgoing packets from the network and either allows or disallows them based off of rules. The firewall can be an individual one that protects a host system, or it can be an appliance which is protecting an entire network. For example, for an individual host, Windows ships with a firewall these days, which comes enabled by default. It's always there, and you pretty much don't have to worry about it. If you've ever installed a game or some other program that has to reach out across the network, you've probably seen a little allow notification that's the firewall asking you if you want to permit the program to do, whatever it's supposed to be doing across the network. An appliance is more of a piece of equipment for a larger corporate network where, say, for example, you want to only allow a couple specific hosts from inside your network to be contacted from the outside, and so you can use that appliance to filter traffic that way. Now, in terms of how you filter traffic, there's a couple different ways you can do it. The most basic way is to use ports where only specific services can be reached. So in the corporate example, if you have a couple web servers, you can set things up so that only your web servers on those particular hosts are available. You can also block traffic based off of destination. Say, for example, that you have some hosts inside your network that there's just no reason that anyone should ever be routing to them from the outside. You can just block that entirely. You also can filter on origin, where, for example, if you know that somebody has been doing malicious things on your network before, either denial of service or something like that, you can just block them forever. Now, of course, that just allows them to move to another origin and then they can attack you again. So often for places that need to stay secure, you'll actually explicitly allow traffic from particular origins rather than having sort of a list of places that you don't want them to be dialing in from. And then finally, a more advanced firewall can filter off of content, where, say, for example, with an HTTP transaction, the firewall can actually go in and inspect the traffic to see if there's some sort of telltale from a known piece of malware or something like that. Now, these firewalls are a little bit more advanced, and of course, this only works if the content is unencrypted. So this opens up a whole mess of issues about should you allow encrypted traffic and when do you want to allow encrypted traffic. But that's sort of a policy thing that we can get into later. Network address translation, or NAT, is one of the technologies we came up with to keep IPv4 traffic viable. However, it actually turns out to be a really great security tool. So let's take a look at how it works. The basic idea is that you have a router on the outside of your network which presents a single public-facing IP to the rest of the internet. So the rest of the world can really only see that one particular IP address. And so behind your router, you have all your laptops, your Roku, your cell phones that are connected to Wi-Fi, all of it, everything, is able to reach out to the outside world. And what essentially happens is as the traffic is routed through the router will set up a port and say, hey, this guy is trying to talk to you. As you respond back, please send to this port. And then the router will forward the traffic to whatever device is on the inside. Now, the guy on the outside has no idea what the internal IP address is of the host. They know absolutely nothing about it. The router is basically acting as a front for that host. And so this is really great from a security perspective because it essentially obfuscates the inside of the internal network from the outside person's perspective. It also completely disallows the outside world from talking to anything on the inside because there's just nothing to route to. Now, there are ways of having public-facing services from hosts inside the network. What you can do is set up an individual port on that outside IP, which will be forwarded to a host on the inside. Just for example, you could have on your home network a web server, and what you would do is set up your server like normal, but then tell your router that incoming communication on whatever port you picked should be forwarded to that internal host. Now, from the outside perspective, all they know is they have an IP and they have a port they can connect to. Anything that happens on the inside, like how you have things set up topographically in your network, what host it is, etc., that's all completely hidden. So they have that one service and only that one service that they're allowed to talk to. And this turns out to be a really effective security technology because, like I said, unless you explicitly allow traffic into the inside, they basically have to arrange to have traffic dial back out. An attacker's goal in enumeration is to first probe the network and try to create a map of all the hosts on it. So what they're doing is trying to figure out what all of the IP addresses available are and all of the domain names that they can resolve. From there, they want to discover as much as they can about those hosts. They want to know what the operating systems are. They want to know what the versions of those operating systems are. They want to know the services, so basically whatever is open to ports on that system, and figure out what the versions are of the software that's running on those services, as well as any usernames that they can gather. Now, this process is iterative. There's one level of access from the public internet where usually you can see, like, yep, there's a web server or there's an email server or something like that, and that gives a certain level of access. But then once you peel the onion further and the attacker is behind a firewall or behind network address translation, they can see a whole lot more hosts, they can see a whole lot more services, and there's another layer to enumerate. And then, of course, once you get inside a host, usually you're behind the host's firewall at that point, and you can see a whole nother set of ports that are available. And so you can think of it more as just a loop that the attacker is continually going through as they penetrate a network and gain access. And you want to look at it from that perspective, both offensively and defensively. One of the most basic tools available to both red and blue teams for enumeration is the vulnerability scanner. For example, Nessus is a common product which is used for this purpose. The basic idea is that you have a piece of software which is reaching out to available hosts on the network and individually checking all the different ports to see what's running, and doing so basically as fast as possible with as many queries as it can generate to come up with a list of services. And then the idea is that the tool automatically create a report with vulnerabilities that are associated with those services. There's really two ways that these tools can run. The first is as an authenticated scan, which is usually the way blue teamers will do things, where they give the credentials to the scanner so the scanner can actually log into the system and do an incredibly deep scan where it's actually checking executables and everything from the inside. Essentially, nothing is hidden from the scanner, and if something is there, it's going to find it. This is a great way to make sure that you have full accountability of everything on your system, that you know all the versions, and that somebody didn't start up some service and forget about it and forget to document or whatnot. That kind of thing happens all the time, and so these kind of scans are an essential part of regular system management. Now, more on the red team side of things, you'll often be running like an unauthenticated scan as part of a penetration test, where you don't necessarily have credentials, you're just seeing what information is available from the outside, and then the penetration testers are then using that to see if they can exploit any CVs that they might find. Now, all of these scans are extremely noisy in the sense that they generate a tremendous amount of traffic, and they show up in the logs very obviously as access attempts. And so, in a true red team engagement, or with bad guys trying to do bad things to real systems, even a fairly rudimentary blue team is going to be able to find that they're being attacked when the scan is run from the outside. And so in practice, red teams that either are advanced persistent threats or are trying to mimic an advanced persistent threat, they're not going to be using one of these. They're going to be going for something a little more subtle. Nmap is probably the most popular tool for red teamers to enumerate a network. And the idea is similar to a mass vulnerability scanner in that you're mapping a range of IP addresses and ports for services, and you do have some scripts that Nmap can run to check for vulnerabilities, but it's not building you a report comprehensively of available CVEs, and there's not sort of a massive database of detectable CVEs behind it. Really, the focus is just on telling you what hosts are out there, what ports are there, and what basic service information it can gather, and then it's sort of up to you as the red teamer to figure out if that information is indicative of a vulnerability. There's a few types of scans that it can run, TCP and UDP, of course, but it can also run what used to be called a stealth scan anyway, where a TCP transaction would be engaged with the service, it would send the SYN packet, wait for the SYN ACK from the server, but instead of sending that final ACK to initiate the handshake, it would just sort of let things drop. Now, back in the old days, as some people might say the good old days, servers were pretty dumb, and they would just say, oh, well, I guess the guy went away, don't worry about it, and then they just wouldn't log it, and so you could do a scan and nobody would be any the wiser. Of course, people wisened up to this a long time ago, and so it's not really so stealthy anymore. Now, something to note is that Nmap is it's less noisy than a mass vulnerability scanner, but if you just run it without any extra configuration, it's still super noisy, and anybody's going to figure out that they're being scanned. There are ways of making it stealthier, but that also makes things much slower. So it's kind of has a very targeted place in red team engagements where it can be used, but it has to be used sparingly, and the utility is somewhat limited by the need to be stealthy. Let's take a look at Nmap in action. Now I've already kicked off this particular scan because it takes a little time to run, but let's walk through the results. First, we configure the scan by saying Nmap. We want it to scan this particular IP address. In this case, I'm using the system lame on Hack the Box. The -p- flag means that I want all ports to be scanned. -sv means that I want to see versions. -sc means that default scripts will be run. And -pn means that I don't want Nmap to rely on a ping scan of the system in case it's been configured not to respond to ping commands. Now we can see the list of ports. For example, port 21 is open and anonymous FTP is allowed. We can see that from the FTP anon script that was run. And we see a couple vital stats from the server that way, including the version number of the FTP server. We can see on SSH, when we connect to it, we might not have credentials, but we can still see that it's running Debian Ubuntu. And we can see the OpenSSH version, so that's very helpful. But the really juicy stuff comes down here, where when enumerating the SMB service, it sees that a vulnerable version of Samba 3.0.20 is running. Now, this is vulnerable to a particular vulnerability that we already exploited in the previous episode. And with that, we can have root access to the system. Now, the vast majority of the time, you're not going to find something super obvious like that. However, it's an indication that sometimes if a system is grossly out of patch or happens to have a particular vulnerability, it can be uncovered with this sort of detection. And even if you don't find an exploit, the service information and the operating system information is very helpful for then developing the next step of the enumeration process. One of the first things to do when enumerating a system after a host is discovered is to try to figure out what operating system it's running. It seems pretty obvious, but this is the first step, and there's some nuance to how you can go about it. Now, the Nmap -o flag will try to guess the operating system from the TCP fingerprint, but it's not foolproof. There's also a few ways to use the specific services to disclose information. For example, if there's remote desktop running on port 3389 on Windows, this is going to give you all the information you need. You can get the host name, the operating system number, and all sorts of other wonderful information. Sometimes it'll give you default usernames on the login screen. It's really nice, actually, for a red teamer if they can get access to that port. For port 22, this is not necessarily a dead giveaway that the system is running Linux or another Unix system, but it likely is since it doesn't come by default set up that way on Windows. And then also with a web server, if you see something running on port 80 or port 443 for HTTP and HTTPS respectively, web servers will often tell both their own version and the underlying operating system version number on error screens. So if you can find some way to induce an error by asking for a resource that doesn't exist or something like that, you can get the information that way. Again, pretty obvious stuff, but this is step one for enumeration. With an Nmap scan run or some other technique done to identify hosts, you want to then map all the ports and services that are available. Sometimes this can be done with Nmap, but in a quieter environment, you can also do scripting to try to reach out to common ports with some program that you've written yourself that has some stealthy characteristics or meets some custom environment. However you do it, the basic idea is to figure out what ports are open and what services are running. You also want to try to find out if a box has multiple IPs associated with it. And when we said before that each system is uniquely identifiable by an IP address, this is true. However, it's not a one-to-one relationship. Each IP has one and only one box, but each box can have multiple IP addresses where the host actually has multiple network adapters that will allow routing from multiple IP addresses. So if Nmap hasn't given a version number for the services that are running, once you have that list of ports, the red teamer will try to go in and grab those version numbers, often by manually inspecting traffic with those services. So for example, if there's an email client, you can just connect to it, and a lot of times the service will just tell you what version number it is. And then from here, the attacker can begin the CVE evaluation process. Now, note, this is just step one. It's not like the attacker does this and they have the keys to the kingdom. Each individual service has its own techniques and its own sort of nuance to figuring out exactly what information is available. And we're going to cover each one of these key services, web services, email, SMB, etc., in follow-up episodes. But just to give you a little taste of what it can be like to look at web traffic, say, for example, that you've found a web server and a domain name. So you know that there's a www.vulnerablenetwork.com or whatever. And you want to figure out, are there other things? Like, for example, is there a mail.vulnerablenetwork.com? What else might be out there? Maybe there's an admin.vulnerablenetwork.com. One of the tools you have available as the red teamer is a DNS zone transfer, where the attacker can query a DNS server and essentially ask for its records. And the DNS server, if it's improperly configured, will give a map of subdomains and IP addresses. Essentially, this is just handing a network map over to the attacker. Now, you as the blue teamer should never have a DNS server just say, oh yeah, that's fine, here's a total map of the network. That shouldn't happen. And it's actually considered in many jurisdictions an attack to even ask for that, to even try to do a DNS zone transfer. So this doesn't usually work. However, I've also heard of some penetration testers who have found even large Fortune 500 companies that don't have this configured properly and have gotten even internal DNS information from an externally facing server. So, you know, it does happen, and it's worth saying that these servers need to be locked down. Another technique that gets used is checking the SSL certificate for a website. So you have your www.vulnerableserver.com, and you want to see what other subdomains there might be. So if it happens to be protected by HTTPS, you can check the SSL certificate, and sometimes that certificate will be signed for use in various subdomains. We'll talk more later about what this really means to be signed and so on and so forth. But for now, just know that the certificate can list multiple domains, and you can, since it has the signing authority to do, whatever the admin subdomain is, now you know that that admin subdomain exists. Now, as a CTF hint, this is something that gets used all the time, where the person who built the CTF challenge will use a single certificate for everything, and so you can just check the certificate and see a full list of all the fun stuff you're supposed to discover. Another helpful tool for red teamers is to simply use context clues. If, for example, a public-facing website just explicitly refers to an admin subdomain, that's a pretty good hint that the admin subdomain exists. Sometimes there's a resource linked from another subdomain, that's a good clue. Anything really can give it away to the attacker if there's an even oblique reference to some of those subdomains. Let's look at a domain transfer in action. In this case, we're going to be using one against Kronos on Hack the Box. So we issue our command, and the results come back pretty instantly. In this case, Kronos has been set up to allow this unauthenticated domain transfer, and we can see several different subdomains exposed. We can see admin.kronos.hackthebox, ns.kronos.hackthebox, and www.kronos.hackthebox. Now in this case, this is just a capture the flag exercise, and so all the IP addresses are the same, it's all the same host. However, in a real-world situation, this would be allowing us to see whatever the IP addresses are for these different hosts, and would potentially discover a whole new element of the network that we were unaware of. All right, now on the blue team side, how do we foil enumeration? So enumeration is an iterative process. Each time the attacker is gaining additional access, they're diving deeper, they're re-enumerating, they're discovering more things, and from there exploiting more things. So we want to apply the concept of defense in depth, where we don't put all our eggs in the one basket of saying we're going to just prevent people from getting in. Let's acknowledge that people are probably going to get in, and how do we slow them down at each phase of the process? And enumeration is one of the first steps of that process. So we want to look at making sure that we leak as little information as possible at each step. So the first step, let's look at this outer layer of the onion from the public world, is our overall attack surface on the internet. We want to keep the services and hosts that we have running there to an absolute minimum. So the fewest points of contact electronically with the outside world as possible, makes for a more secure environment. Now, once someone is inside your system, like say they've gotten through that first level firewall, they're inside for some reason, you want to keep the same principle in mind. So once you're inside a network, obviously you have a need for more services. You need like an FTP server internally, you've got your Active Directory services and all that good stuff. But you still want to make sure that everything you have running ties to a real business justification. If it doesn't have a reason to be up there, then it shouldn't be, because it's just contributing to attack surface, and it should probably be retired. Now this extends to even within a system. So say, for example, you have a web server that's talking to a database server, and they're both running on the same host. And nothing else is using that database server. It's just being accessed by that web server. Is there any reason that that system's firewall should allow anything that's outside that system to talk to the database server? Probably not. If there's no workflow for it, then it can be disallowed. And this just makes the attacking of that database server much more difficult if the attacker has to be inside that system in order to get to it. Basically think about creating the onion as separated as possible so that each service is only visible to the most minimal extent possible permitted by your business workflows. Also, even within a system, just within a local host protected within a firewall, only allow minimum essential services to be installed and run, because once the attacker is in there and enumerating at whatever level of permission they have, they can get in and they can use that to do malicious things. Now you might think, well, they're already inside the system, what does it matter? Remember that a key part of the process down the road is going to be privilege escalation. And so just because they're inside at some low level of access and they have some level of code execution, that doesn't mean the game's over yet. And so you want to do everything you can to slow them down at each step of the process. There's a few other practical takeaways that we can gain from the information we have today, although we'll get into a lot more detail as we talk about specific services and how they're enumerated later down the road. For now, let's remember to secure our DNS records. This keeps information leaked to a minimum. You also want to have separate internal and external DNS, since external DNS servers probably don't need access to the records for your internal network, and if they're compromised, then you've just given away a whole lot more information than you need to. You want to manage certificates carefully. Issue certificates for specific servers and services that then don't provide a map of your network. If you have one certificate to rule them all, which has a list of individual services it's authorized for, then you're just handing to the attacker, here's a list of all the stuff we got running, go at it. Probably don't want to do that. You also want to limit the information that's available on service banners. Just as an example, if you're connecting to an email client, you really care about the protocol, not necessarily the software implementation behind it. And so telling the attacker what specific version you're using is just asking them to come up with a CVE list for your system. One of the key concepts is test whenever possible. Don't assume that you applied your system hardening correctly. You want to actually try to use the offensive techniques that we explored in this module and actually see if you did it right. Like try to test out your own system, run Nmap, and just see what's running. A key part of testing your system regularly is the vulnerability scanning. Really, you should be doing this at a regular cadence, and often it'll be a requirement for a new system to be activated. Say, for example, you're adding new hardware to the network, just make sure you scan it first, make sure it's all up to date. Remediation for issues is often tied to a regular patching cadence, where you have a scan done and then you have to patch everything that you found at some frequency depending on severity. So you might have a requirement that any critical items get patched within a matter of days. Medium items, maybe you get to that within 30 days. It sort of depends on your system posture. However, oftentimes in this scanning, you'll find things that are harder to fix. Like maybe there's a configuration setting which is not secure, but it's also been integrated into a business workflow. And if you turn it off, then suddenly your company stops making money and you have a really bad time. So a lot of times you'll develop what's called a plan of action and milestone, or a POAM, where you have a remediation plan for that issue tied to some specific date or milestone or something like that. So you say that when you run a scan, we found a vulnerability, we can't fix it today, but we have a plan for how we're going to do it. And then there's accountability within the organization to figure out that there's at least a path to get that fixed, and you can hold people to getting that done. Now that we've talked, at least on a very, very basic level, how vulnerabilities can be found, let's figure out how bad guys exploit them. One of the key ways that they do this is to generate malicious payloads. And so, from the red team's perspective, we'll be talking about what tools they use to generate these payloads for an engagement. And then on the blue team side, we'll talk about antivirus and other techniques that we can use to mitigate the risk of malware infection.